the schematic overview of rendering, what we're going to do is look at this thing. So this is definitely not everything, but it's the most commonly used ones, the most powerful ones, the most visual ones, you know, the things we've prioritized. And actually, let me give you an overview of this first over here. So again, we're starting with ahead of rendering. Just a quick word about that. This is ahead of rendering. Then the visibility in the blue box. Rendering starts over here. Just mentioning there is an early Z pass, but in reality, it probably doesn't impact you, but just going to mention it. The base pass will be rendered with draw calls. All the different mesh types will come in. There's dynamic instancing we have base pass material. The light mask comes in. The light maps were generated by light mask, which impacts all of this. We're going to look at different things that light mask does. It renders out the GBuffer, which is made up of these 5 buffers. It then brings in dynamic lighting and shadow, which is actually a very big mix of different features. And it will end up with reflections, which is 4 different ways of doing that. We'll have various additional things here, a couple of things to mention, especially translucency is always a challenge in real time and in game engines. And various post-process settings, and it ends up on performance. We do have a scalability example here as well we want to touch on later, but that's all we have. So let's start with ahead of rendering plus visibility. It's important to note, and this is going to be a very small picture, it's going to be hard to see, but before we even get to rendering or occlusion, visibility, anything like that, the CPU has actually been calculating everything that has nothing to do with the rendering, right? So the physics, the animations, anything that basically has to do with positions, I would say, like, you know, the positions of things. So a skeletal animation is the position of things, of the vertices where they end up, because the bone deforms them. Physics moves things around, gameplay moves things around. So everything about figuring out where and what's where and what's to be rendered in the first place.
Yep.
So that happens ahead of it, but that happens one frame earlier, because the CPU needs to calculate it and then write the result. By writing the results, it needs to just say, okay, this is my result, and then someone else, the next thread, needs to take over on that result, which means this has to be finished, which means that the next frame can only start doing that once the CPU is done with 1 frame. So it's 1 frame behind. That next frame is the draw thread, which has to go over the visibility essentially, and then the GPU takes over in turn again. So the GPU is 2 frames behind on what happens. So if you press the button, there is a 2-frame lag between you pressing the button, that having been reflected in, I would say, the CPU, you know, what the CPU has calculated should happen in the game because you press the button, and the GPU actually getting to rendering it, because it needs to load the information from one section in the hardware to the next. So just so you're aware of that. But visibility. The visibility process in Unreal is, what is it, 5 steps, I think, 1, 2, 3, 4, 5, or rather 4, because this is the whole thing in general. So 4 steps, and they're staged. So it always starts at the bottom, and it tries to do as much with the bottom one as it can. And then it goes to the next one, tries to do as much with that one as it can. What it tries to do is it tries to cut down the number of things that have to be calculated here, because that's the most powerful one, but also the slowest one. Okay, so that's how it stages through it. So the quickest and easiest and fastest one to do is one we have here at the bottom, which is distance culling, but it's not enabled by default. So I pretty much always set this up, even in indoor environments. Distance culling means nothing more than this. If you press G to be in game mode and you fly away, you know, stuff disappears, you can see. You know, like if you look at the building, things, especially the railing at the bottom, it's disappearing. I'll quickly do this just to pardon the landscape loading, but so there's a property in here, in every mesh, in anything that's rendered, that says draw, I think, maximum draw distance, desired max draw distance. If you go further than that distance, it simply disappears. Because you don't want to set this for each and every single model or mesh or anything rendered, that would be annoying. You can use a cull distance volume, which automatically does that for you, which is this one. So you place the volume around it, you enable the distance in it, and it will calculate a model that is between this and this size will be culled at 4,500. If it's between that size and the next number, 512, I like power of 2 numbers. It's a long story. But then it will be culled at 7,000 and so on. So it automatically then assigns that to anything in that box. So that makes it much easier to mass assign these values. And you should always do that because this is very easy for the for the hardware to figure out, it's that far, let's just not render it. And then there is the frustum culling. So again, standard in game engines, of course, it's a bit difficult, can't easily visualize that, but it figures out what's in front of the camera, we render that. What's not in the field of view of the camera, we don't render that. So that's also easy to calculate. That's standard enabled, and I don't think you can even disable it, even if you'd want to. Not in an easy way. Then we get to pre-computed visibility. That's not enabled by default. It's not always used either, as we can see over there. Okay. What you need to do to enable it, and it typically works best for mobile devices, or maybe certain consoles, perhaps in certain
let's say when you have more memory than performance,
sure,
it's usually useful to have it.
Yeah. So I can do show visualize pre-computed visibility cells, and we got this. So each of these cells is remembering what is visible in that cell. So if the camera enters a cell, the camera will ask the cell, hi, I'm inside this cell. Can you tell me what you've stored in your array of what's visible? And the cell will say, yes, you can see this. And then it's part of that occlusion process. That is pre-calculated because there is a volume here again, a pre-computed visibility volume, which is that one. You can see the blue boxes correspond to that one. So that's there. And that one in turn is pre-computed actually by light mask, strangely enough, because we're using the light calculations to do the visibility checks as a quicker way of pre-calculating this. So you gotta bake the lighting to get that working, and it's gotta be set up in the world settings. Somewhere in here it's going to say pre-computed visibility, right there. Enable, and you can set the cell size to smaller, more precise, more memory. The height of the cell can somewhat strangely be set in the light mask config file. And you can only set one size. So it's a bit of a limited system, but it works very well, again, for limited memory. I do tend to set this up most of the time, even on PC, just to try and shave off a little bit of the occlusion times. Then you have the actual visibility culling. So this is the real one. This is the one that's enabled by default, and that typically does most of the work. So it's also the heaviest one, which is why these other 3 steps try to reduce this as much as possible. Visibility culling, by default, hardware occlusion visibility culling, means that every mesh will act as an occluder for everything else. So you can visualize that with a not super well-known command. Sorry, it's one of the buttons got stuck, it seems, in the editor. If, for example, I position the camera behind the tip of the wing, and I try to get as close as I can without going through it, something like that, and you type at the bottom, it's called freeze rendering. It's not even suggested, and it's not even accurate because we're not freezing rendering, because if you would freeze rendering, the whole screen would just freeze. We're freezing occlusion, but if you enter that, you can see behind it, this is no longer rendering. So now you can see what's no longer rendering. This is what's actually still being rendered in that angle. So every mesh hides and occludes what's behind it, pretty much entirely accurate. And that's an interesting feature. That takes most of the bulk of the occlusion work to figure out what do we render, when, and how. But it's also slightly heavy. It's not massively heavy, but it takes a bit more performance. On certain platforms, particularly mobile, I think, I'm not sure actually if we can do hardware occlusion on some mobile hardware. I think we can. But in any case, majority of time, there is another thing we can use, is software occlusion, because this doesn't work on all devices. Again, certain mobile devices might be a stretch, might not be possible. So software occlusion, look at the slide for this, is a second system that kind of does the same. It would use a lot, so a mesh lot, so you would define which lot to use as occluder mesh, and it would use that one as an occluder. So you define the occluders in the world by using the lots, and then you use a software occlusion to try to figure out what it should and shouldn't render. But again, that's typically not very often used, but it's in there. Okay, and then we end up with occlusion. So now the renderer knows, first of all, it knows the position of things, and it knows what exists in the world. If a gun has been fired, or a cannon rather, so the projectile exists in the world. So this now is included in the list of things to render. This one calculates what can actually be seen, and now we can start with actually rendering that. So 2 frames later, we ended up over here, and we're going to go through the rendering process itself. Okay, so we're going to get to the early Z pass and the base pass. The early Z pass, I just want to mention, just so you're aware that it exists, you don't typically change it or do anything with it, but it will render the scene depth, and it does, so the scene depth is the Z. The Z is the depth in this case, so early depth pass. There's settings you can modify for that, again, not typically done, but just so you're aware that it's there. Because if we know the depth of the scene first, that's important information we need as we continue rendering. So in the project settings, you can say early Z pass and you can say how it should do it. But again, for certain particular cases, you might want to look at it. But other than that, just mentioning it. So that's there. And then we move to the all-important base pass, which is one of the biggest steps of the rendering. So the base pass is the initial rendering pass it goes through, which in turn is doing this. First of all, it takes all the things that are 3D and have got to be rendered. So that list I've got here is not exhaustive, but you get the idea, primarily anything 3D. So we'll take a static mesh, maybe it's an H-lot or not, but all of that stuff will become a draw call. So now you can see a little bit how that works. There is actually, I'm not going to show it today, but there is a plugin you get enabled for RenderDoc, and then you can download an application called RenderDoc. It's a free application, you can download it. It will tie into Unreal, and it will capture the data and the way the GPU is currently rendering it for one particular frame. So you can look into where exactly the draw calls are being rendered. You can literally step through each and every one of those draw calls as you go through.
Even read the shader.
With the shaders, with the materials, and that is the base pass. So the base pass is the act of rendering all the pieces of geometry, because when it renders, it will do a draw call per draw call, right? So it will render, here's one draw call, one pillar is a draw call, the next one, the next one, the next one. So that whole thing is a base pass.
Why don't you show it in the GPU profiler? Like the how the picture is of a frame and what's the importance of the base pass.
Sure. So if you look in the GPU profile, you get an idea of everything the renderer does. This is that same list. And we're currently, again, we skipped a few things.
Yeah.
So we skipped a few things here, but there's going to be an early Z pass in here, but we're now currently at the base pass. This is the big one, right? And you see all the meshes, each of them is in here. It's a draw call, and how long that takes to render that particular one. It also is going to do a first pass on the materials that are rendered on top of it. Because it's a deferred renderer, it can't render all the material stuff at once, but it's going to do that first pass, which are the base pass materials. So that's minus some of the reflections and such blended in, but it's at least, the basics of it, right? Including also the light maps. Now, before we explain where the light maps come from, just mentioning this too, we do dynamic instancing. It's something that's enabled in Unreal Engine by default. So by default, it's actually going to try to take similar meshes and render them at once, batch render them. So
all the same meshes and that share the same material instance will be batched and rendered as one draw call.
Plus meshes, static meshes at least, they're also batched in memory anyhow. So you only load one single pillar, no matter how many pillars you're rendering. It's only there once in memory. And indeed, with that feature, it's also rendering them as one big chunk. But the light maps are coming from an application called light maps. That's a separate application. So when you run build lighting only, and we don't have it running over here. I'm not going to build a level for the sake of time, but it's going to open in the bottom. It's going to open
Swarm agent.
Yeah, Swarm agent, which is the agent application of light maps as a system. So you got a Swarm server and an agent. By default, your computer is also the server, so it just builds on its own. But what it would enable you to do is have many computers in the office or wherever you are, have the agent running, and one of them is a server, and you have essentially distributed rendering, so it can divide the work across the different computers. But that application controls the building of and the baking of the light. Okay. That means that we take any static light actors as placed in the world, and again, the light mass importance, volume. It takes those into account, it goes in there. It will bake using global illumination radiosity. It's essentially any modern light baker, it does the exact same thing. It all goes in there. But more specifically, we've got these two. So it's also going to bake volumetric light maps are the current default. Volume lighting samples is the same thing, but the older system. But it's still in there. it takes less memory, it takes less GPU time. It tends to work better for low-end hardware, so it's still in there.
It's less accurate.
Yeah, it's also much less accurate. So you can see this over here. If you're in the viewport, we can do show or visualize thing. Visualize volume lighting samples, old system. We don't have that in this one. We're using the newer one, so volumetric light maps. And the world is populated by this grid of spheres. And they only exist within the light maps importance volume. It's not 100% accurate, so you can see it actually extends outside of it here and there. It depends on how it's storing the volumetric light map, so sometimes it needs to go a little bit outside the edges, but it's placing that inside the volume. These things are really important for dynamic meshes, so anything that's moving through the world, maybe a character, and the character needs to understand what the baked ambient light was, so the indirect lighting that was baked into the environment. It doesn't know that. It needs to know that if the character stands near this fire, and the fire is baked in, the character needs to illuminate itself. But how do you know that when the lighting is saved in just textures, the light maps? So it also saves the light into this grid of spheres. And then as the character goes through the world, it reads the information of the spheres it's nearest to and shades itself with the color it retrieves from those spheres. It's a volumetric light map. It captures it from the lighting from multiple angles, so you get really nice shading on it. The other system does the same thing, it just does it much more simplified. So the volume lighting samples would have done the same thing. The world is populated by a grid of little squares, but every square has a single color only. It's much less precise, takes less memory too. And then we'll move into, before we go there, the GBuffer and then dynamic light and shadows. Right, so all of this results in the GBuffer. The GBuffer is nothing more than the base pass rendering itself through a couple of different versions of the frame, right? So you got buffer A is the world normals. So now we have rendered in the information about, which direction does every surface point to? Because if you know that, we can use that for other things later on. It's got a buffer B is the specular, roughness, and metallic together, and we can visualize this in the editor, which I'll do in a second. Base color in itself, and base color plus lighting, by the way, which is not displayed here, you can do because of that as well. There's another buffer here, another buffer there, holding additional things. So the GBuffer is nothing more than 5 images that got saved out for every frame that we can then base the rest of the deferred rendering on. In the viewport, you can see this as well, because you can do buffer visualization, and you get a bit of an idea of the different information that's contained in those buffer images. So based on these different versions that it has rendered, it can do the rest of the rendering. But then we're ending up with dynamic light and shadow. So as with any modern real-time renderer at this point, a lot of the features that are in there are very specialized often. Okay? So there is not just render shadows. Rendering shadows is actually made up of this whole patchwork of solutions, because to render shadows indoor is entirely different than to render shadows outdoor. They pose very specific challenges. So what we need is this, again, different solutions doing very specific things. And we got quite a lot of them. So these are all the different ones we've got. And they're divided between direct lighting and indirect, and between light and shadow and light and shadow. So it's 4 different groups. So let's look at some of the features of the engine. We've got IAS profiles. If I remember where I put that one even, let's see, I can probably just make a new light. Probably just take a spotlight, put it to movable. And there's a property in here that says light profile, IAS textures. Okay. Now I don't get anything in here, but I believe the engine folder, so I'm going to show engine content. There's a couple of things in there that I can just click on, and you can see kind of what happens. It's add a bit of structure to the light. So an IAS texture, it is a texture, but it's not a normal texture. You can see if I click it, it doesn't help. You can order these. This is a standard industry format that is also used outside of the games industry, so there's nothing really to do with Unreal, but it's a standard format that you can use to order the, how would we describe it? The fall of the shape of the light as it's being cast by where it comes from. So for example, you can use that to make it better fit the light fixture. If the light fixture has some glass surrounding where the light actually comes from, right, I might distort and refract the light as it goes through it. You can use this to get close to that.
Like the light that Unreal provides are perfect lights, perfect point lights, but you never have that. Like if you have a light bulb, it's going to, like the glass is going to deform the light in a way, and that's the IES.
Now, for sake of being completely transparent, I have this placed here in dynamic light and shadows, but this actually can also be baked into static lighting. So, but I had to place it somewhere, so it's not entirely accurate where it's currently placed. Then you got light functions. That's very similar, but even more powerful, I would say. This is a really fun one. It allows you to take a material that is blended with the lights. I'm going to delete that one, and I've done this, for example, for water. You can see the water caustics we have. It's a very simple effect here. A lot of these things in this example environment are very simplified and basic, but this is a basic version of what a water caustics effect could look like. We've got two spotlights here. One is pointing up, one is pointing down. Take that one. And you can see here, it says light function, and here's a material. And this simple little material, you can see it's very simplified, creates this effect that is then blended. You can see the material domain has been set to light function. That is then blended on the light, so the light is actually causing that. We use this for fire flickering, water caustics. You can even assign it to the directional light and have the clouds themselves cast shadows on the world. So that's super cool. Somewhat, it adds a performance step to it, but it's super cool to actually see the shadows drifting over the landscape. And by the way, make sure you set a fade distance to it, so it removes the effect at a certain point. Because that takes a little bit of performance too, so it always helps you to cull that out. This is dynamic only, by the way. You definitely can't bake that. So those two are to do with light. But then shadows, again, shadows are much more complex. Shadows are typically heavy to render. So you got the normal dynamic shadows, just a standard dynamic shadows. Typically, by default, they're being cached. So we're doing shadow caching. This is the reason why in Unreal, if you have a lot of point lights, for example, or other kinds of lights really, but in this case, let's say point lights, like I did with that one right there. It's a movable light, and it's casting a shadow. You have a very harshly defined shadow here at the bottom. If you have a lot of these lights, it's still going to run pretty well because these are cached. Until something starts moving, then it invalidates the cache and you take a sudden performance dip. So to be aware of that, I believe you can toggle that and experiment with it. There's a command for r.shadow cache whole scene shadows, so you can work with that as well and see what the impact is of it. In fact, I'm wondering if I dare to do this. Let's see. Let's experiment a bit. I'm currently 46 frames per second. If I were to say that whole scene shadows is off, and in this case, I don't think that will do much. I only have a single light, but you can experiment with it and see what happens. Typically, you don't want to turn it off, so just highlighting it's there. Then you've got cascaded shadow maps. So cascaded shadow maps are specifically meant for outdoor environments, as we have over here. Because the challenge with shadows is, because they're so heavy to render, you don't want to render them across the entire landscape. That would be a problem. So you need them to disappear at some point. But just disappearing them would also be a problem, because that's rather ugly. So you need them to gradually disappear. And in a way that saves as much performance as possible. So that's where a cascaded shadow maps comes in. Cascaded shadow maps is 3 different shadow maps, and they're cascading. It's 3 different: low quality, medium quality, high quality. By default, it's 3. And they're disappearing over a distance to try to ease it out. I've set the shadow distance very up close, and I think if I'm right, the fence here, I've made sure that it's going to be very visible. So let me verify this. I believe one of these fences. Let me verify the setting here. Yeah, you can see right there that's disappearing. So that's where the shadow, the cascaded shadow map disappears. So that's set on the directional lights. That's the default way we're doing things. There's the directional lights. You can see the section here for cascaded shadow maps, and it's set to 2048 again, unlike power of 2 numbers, but that's it. And you can see it has by default 3 different cascades in there. Okay. So that's one feature. So these are the 2 standard ones, but then we get to the more specific ones. This has a problem in that A, it's still heavy to calculate, it's still heavy for performance, and B, it's still ugly that you see shadows disappear. So we've been working, a couple of years ago this was introduced, to try to improve that. And these are distant field shadows. Because the real challenge with rendering shadows is that you got to consider the geometry for the shadow map. And considering the geometry is heavy. But if you were to be able to figure out the distance between points without considering the geometry itself, but by just looking at some pre-calculated piece of information, let's say a texture, it would be faster. So if you were to be able to put the shape of a model into a texture, it'll be faster. And that's the distant field. So distant field is essentially a hologramic, I guess, you want to call it like that? I don't know.
It really, it's a function that defines the shape of a model. So having a function is easy to know. This function will always tell you how far are you from that surface. So that's used for ray matching. That is going to be much faster. Having that information is going to be much faster and can be done quickly.
Yeah. And so you can enable this. It must be enabled in the project settings. So by default, it's not. You enable mesh distant fields, or distant fields, it's called, I think, by default. And then you can visualize it, and it looks like this. So this is the representation of the world with distant fields. It's not very precise, as you can see. It's not particularly precise, so you'll get some precision errors. This is why we only use this for distant shadows. But in the distance, the shadows will start working with this instead. And we can have much, much longer shadow ranges. And that is also what's happening here. You can see on this mesh, I disabled the distant fields. So as we move away, the shadow disappears there. But on the other balustrade, it doesn't happen, see? At this point, the other one takes over. And if you were to look very up close, you would see it's not very precise. There's a hole in the shadow in the middle of the railing. That is because, again, the distant field is not precise. But it allows for much longer shadow ranges. Now, again, for testing purposes, to visualize it, I made it disappear very quickly as well. But normally, that would now run for the next 20,000 or so units.
Yeah, it's cheaper, but it's
imprecise.
Imprecise.
And it costs memory because you got to store the mesh distance fields.
Yeah.
But still, it's an important part of what we do in the rendering because this is used a lot. It can, in fact, once you have this, be used for other things. It can be used for material effects. Nothing to do with rendering right now, but you can use it, for example, to figure out if a model is coming close to the ground. If it comes close to the ground, it gets maybe wetter or something. So you can use it to make material detect surfaces around it. You can use it also with dynamic shadows, normal dynamic shadows, and make them soft. It's not going to be super precise. I mean, it's not super realistic, but it's definitely much softer than the default very hard shadow.
It doesn't work for skeletal mesh.
Yeah, it's limited here and there, but it's a step forward.
But it's also important for ambient occlusion. It's going to give a cheap ambient occlusion.
That's we'll get to it in a second as well. So it also does that. So the distance field do quite a lot, but you got to enable it by default. You got to enable it. Don't have an example of this. Speaks for itself, but there is also ray trace shadows. Ray tracing in general in Unreal Engine got added in. I'm trying to remember. When was that? I don't think it was GDC last year, right?
Yeah.
I think so. I think that was around March 2019. I think we added the first public version of ray tracing. So of course you can do ray trace shadows. It's all there. You can also blend that with all the other techniques. You can scale it. You can enable it on a project. Disable it on the fly more or less. So it's completely integrated with everything else. There's no difference, no different builds needed, no different, make it exclusive, ray tracing only, or everything else. No, it's just part of the whole thing. Then you got per object shadows, and actually you've got inset shadows, and I believe, I'm not 100% sure, I'm always confused by this. I believe they're actually nearly the same or the same. Okay. Yeah. In any case, you use these often, but you very seldomly realize you do. But what both of them do is it casts a limited size shadow map. It tries to improve the shadow quality, if you want to have the actual outcome of it, locally for a particular thing. So it's typically used for characters. If a character needs to have a nicer shadow, you have a per object shadow, inset shadow. The per object shadows also tie into if you've got a light. Let's see if you have a light here. I think it was that one. Yeah, if you put a light stationary, I believe that is also a per object shadow that it then does, because it will bake the lighting into it, it will bake the light map into it, but it will also render a nicer shadow on top. I believe that is a per object shadow. Likewise, again, for characters, it would allow those characters to have nicer shadows. You can see here's a dynamic inset shadow, so that's part of those two things. In fact, let me try to see if we can visualize again. Improvising on the spot is probably not the best idea, but what could possibly go wrong, right? So we got the mesh here. I'm not sure if that's going to show up. It's probably on the character, so it's going to be very hard to see as well. In this case, we won't see much, but that option is there as well. And there are context shadows. I personally never use them, but it's a feature that's there. It's actually, probably to be correct, this thing should probably be in post-processing because I believe it's entirely screen space, correct?
I don't know.
I think, okay. I believe it's entirely screen space, so technically it should have been there, but because it's part of the shadows, I put it on the left. But the context shadows, I don't have it set up. It's a screen space effect where it tries to create tiny context shadows behind surfaces. You know, I'm not sure if I have an example in the room around me here, but you know, if for example, actually the cable, we've got a cable over here. There's a tiny shadow right under it where it's near the table. That's too small and too precise for some of the other techniques to catch. So that one is tried to, in a very cheap way, screen space, draw a black line under it. And you know, in my experience, it's kind of hard to get it right, and you know, it depends really on the content. And then those are all the shadows features that have to do with direct lighting. But then we also have indirect lighting and shadows. And so when we look at light there first, there is a light propagation system. This is an older system, and it's meant to give real-time global illumination. What does it even do? It makes cells or voxels almost, or do you know how it's? No. Okay. But in any case, it is definitely, I would say, outdated. It's several years old. Feel free to experiment with it, but I would probably not recommend any production use of it, unless it's very limited in scale. Then there is ray trace GI. So again, all the ray trace capabilities are in there. They're all blended with all the other techniques. So if you wish, you could use ray trace GI. It's heavy, obviously. It is a complex thing to do. It's in the engine. But neither of these two are typically used in games right now. Right, so this is not that commonly used. The shadows, on the other hand, are much more commonly used. This is basically used, these two are used nearly all the time in most outdoor environments. So the ray traced AO, we can immediately, again, go over that. It's, as the name implies, it's AO, but ray traced. Feel free to use it. It renders very fast as well. It looks great. But it's ray tracing. But for normal non-ray traced rendering, we've got capsule shadows. Capsule shadows are a greatly simplified shadow to try and gain performance. This works on any skeletal mesh. So you can see we got this enemy here. The enemy actually has a physics asset. Where's the physics asset? Yes. That one, I think. Or that's a different enemy, which might compile shaders.
Yeah, I always double click on the details panel.
Yeah, it's going to compile shaders, but you can see every skeletal mesh has simplified collision surrounding it, right? So instead of using the actual model itself for the shadows, which is again heavier because the shadows need to use all the information from the model, like these are the polygons and all that kind of stuff. It's heavy. We can have the shadows use the simplified collision, the collision itself, instead, which is a property we've got over here, which is sorry, what was it called? Capsule shadows, right? Capsule shadows, you can do this, and you can see the shadow really simplifies, but it's good enough for small critters. So if you have for example, a game where you have lots and lots of soldiers or units or animals, I don't know, anything really, it probably gets quite performance intense to just render all of them at normal.
And anywhere where you don't have really intense lights, it's going to be also very useful.
So there's that one. And lastly, and I can't show this in this particular example because it needs to have a movable skylight, I believe, for stationary. But you can have a distant field, DFAO, so distant field ambient occlusion. So you run ambient occlusion, and this tends to be large-scale ambient occlusion much more than anything else. So it's not very tiny or precise ambient occlusion, because you can see, it's might be hard to see, but it's actually a bit of ambient occlusion right there. It wouldn't do that kind of stuff, but it's going to do the very big and important stuff. Again, I can't show it here, but it would be about the skylight. The skylight is set to static, doesn't work then, but if it were to be stationary or movable, it would have the section over here for distant field ambient occlusion enabled. You can see it's disabled right now. You can set the range there and some other options. This then uses all the distant field meshes in the world to shade its ambient occlusion, and again on a large scale. So it's meant for outdoor environments. It doesn't otherwise, it's probably not going to do much. And it's meant to ensure that if you've got a cave in a landscape, the cave is actually dark inside, even if no shadow is rendering on top. So it actually darkens the entire cave. So it's really, really cool, because without that, it just wouldn't look great.
You have to know that if you are using this mesh distance fields for that, you shouldn't be changing the scale of the actors.
True.
Too much.
So indeed, that is a very particular tip. But if you're really relying on distance fields, the scale of the meshes should remain uniform or as much as possible. In this case, that is not
closer
really the case.
to 1. Yeah.
Yeah. So just be aware of that. And while we're on that subject, if you do not do that, I believe you're going to be able to see it anyway with, you can see here, these meshes, they are actually, this one is actually still okay, but at times they get a bit transparent and it starts getting weird like that. I mean, that's not really the way it's supposed to be if you're going to rely on this. Because you can see this is a weird scale, this one is negative, this one is that, it's weird scales. That's not the best idea. So that is one thing to be aware of. And those are all the shadows. Then you have reflections. It's three different features in there, plus ray tracing as optional, additional, or replacing layer. So the reflections, they're a stacked setup again. So it starts off with this one because that's the easiest to render. Then it tries to run any pixel that needs this, and then it replaces any pixels that runs on this. So it stacks it up again to try to minimize the pixels that pass through the most expensive last stage. So the cheapest and simplest thing is by far reflection captures. And we have that over here because we've placed these things everywhere. So the sphere reflection captures, as we have them from the panel over here. Within this sphere, the pixels that are within this sphere are going to blend in the cube map that was captured at this spot. So this simply does a static single cube map capture. It stores it in memory or on disk. And then the pixels will blend it in. The pixels over here will blend in like 1% or something, and then it gradually fades in the closer it gets to there. Therefore, it's kind of not super easy to see, but the reflection we have over here is more or less accurate because it was captured over here, more or less represents there, right? But it's never super precise. We tend to place a lot of these through the world. The way I tend to work is I place very big ones. You can see this one is big. It has a range all the way until here. I go through the world and I place these big ones somewhere in the middle of the room, and they act as a general fallback, so at least stuff is there. And then I place detailed ones with a small radius near very reflective things, and we go on. But again, the faster render, not very precise. So the next stage that would take over, image, are the planar reflections. Because this doesn't work very well for a surface that is very, very, very easy. It's like a mirror. You really got to see it's just not accurate. So planar reflection is much more accurate. The floor here is a planar reflection, and therefore it correctly matches the position, almost matches, not 100% either. Let me check if I enabled it. I might have disabled the planar reflection. Yeah, actually, this is disabled. Actually, it shows exactly the problem now. If you look at it's might be very hard to see on the video. The pillar is here. It doesn't line up with where the pillar should be. If I enable the planar reflection, it does line up. So I get a more precise reflection. The planar reflection, it only works on a limited surface that is completely flat. So the floor is great, wouldn't work on the walls, wouldn't work on these metal, whatever you call these things, the signs or whatever, the decorations. It only works on flat surfaces, but it works great for that. It can also work in real time, capture every frame. Not a good idea for performance, but if you need it, it would do that. Whatever pixel can, however, be rendered by SSR will be handled by SSR. I'm going to disable this again and go back. And you can clearly see this. If you move the camera down, and this is for every real-time renderer, the reflection is changing. In fact, this gets even more extreme when you put it to reflections, and it does this. See, what we're seeing right now, that's the cube map as captured by the reflection capture. What we're seeing here is SSR, so screen space reflections. So it attempts to render the reflections onto the environment by looking at what we had already rendered and in screen space, try to work it out. But that means that if we're not looking at something, like if you look down, we can't see the sky anymore. The sky disappears and falls back to the fallback, which was the reflection capture, or possibly the planar reflection. So that's how it works. So screen space is there by default. These two you have to place in the levels. So make sure you place them in the levels. If you're working with screen space reflections, you can always tweak the quality, by the way, in the post-process volume, or there are various SSR commands to set the quality. Good. And again, ray trace reflection there as well. I don't have an example here, but that would layer on top of it in turn. Good. There's a few additional things. In particular, translucency and atmospherics are very interesting or important to note a few things about. So over here, additional. And if you start off with the atmospherics, there is atmospheric fog, exponential height fog, and actually the sky and atmosphere one as well. Right. So you got sky and atmosphere, exponential height fog, and atmospheric fog. The height fog one is the simplest one, exponential height fog. It will fade out the fog in distance and up. That's it. You can have two different colors, different types in one nowadays. But it's a very simplified version. It's actually what we're using here as well. So the fog you see in the distance is nothing more than height fog. That is that one. Atmospheric fog is a system that tries to make render a bit more complex fog than just just the flat color, which is what the height fog will do. But nowadays the sky and atmosphere basically goes in that same direction, so I think it's it's more or less similar. But the exponential height fog has the possibility to do volumetric fog, and that's where it gets really interesting. So you can enable volumetric fog on a normal atmospheric, exponential height fog. We've done that over here. You can see volumetric fog has been enabled. And just for the sake of being able to see what we're doing here, I'm going to make it incredibly foggy. I'm going to do something like this. And inside the building, however, the fog is actually darker, and over here it actually colors. So the volumetric fog will read the volumetric light maps. It will also read from those. So it colors itself by these same things. So if you're in the shadows, the fog is actually shadowed by the trees. It will also render dynamic shadows on top. It's very hard to see here, but with these shadows. But for example, the sun would be easier to see. Again, maybe you need to go more. But you can kind of see the God rays here. You get God rays, so it's actually rendering shadows. This is the shadow from the building itself rendering on the volumetric fog. It's very cool to see. And the lights also illuminated, so they illuminate, even if they're dynamic light. This is dynamic light, it illuminates the fog locally. And not only that, bring it down a bit, you can also create particles that tie into that essentially you use a particle editor to order a system that creates volumetric fog. Okay, if I enable this one, this auto activate is off. I got a local volumetric fog cloud with some additional complexity in there. And this also receives shadows, dynamic shadows on top. It also reads the volumetric light maps. It does all the other things, that we just mentioned. So that's a nice and powerful feature that really adds to the quality of it. But it does largely rely on static lighting. Without static lighting, it works as well, but it gets a bit more simplified. You lose some of the smaller shadowing in corners and all that kind of thing. Okay, so you got volumetric materials as applied to the particle. That's that one. It's actually all done in the material system. And you get normal distance fog as is part of exponential height fog. They together create volumetric fog. And they also in turn tie into the physical-based sky system. We've shown that in the world building class. I'm going to leave that. On the other side, we've got translucency. Now, translucency is always difficult to do in real time. It's always challenging. There's so many things to think of. So in Unreal 2, we have a number of different solutions in place that you should probably be aware of to move forward. Starting simple, we've got refraction and translucency. There's two different ways of doing that. Two different settings in order to be more precise. Let me first get rid of the the fog in. Sorry, actually that was 0.2. I think the other one was not. What did I have? 0.005, I think, something like that. I've got under the ground here, I've got a couple of test planes. This is a piece of glass. Let's look at the material. Very simple material, but it's primarily in the properties on the left. If you do refraction, which this one doesn't have, but you can put a Fresnel on here, you can put a value on it, just a constant. Just be aware of the fact that there is a property here called refraction mode, pixel normal offset, or index of refraction. It's two different ways of rendering it. If it's a flat surface, like a body of water, like a water surface, it should be set to pixel normal offset and not index of refraction. Index of refraction, I believe, is more for a glass or some 3D object that's placed somewhere. So it does that, but the key thing we really want to get to here is this, because that's where it gets complicated. When you set up translucency in Unreal, you've got a whole number of options. Like as we are seeing in the material class, you can set the blend mode and the shading mode. And obviously, if you make the translucent material unlit, it renders by far the fastest. But let's say you do need lit translucency. So this one is set to default lit. And there's a section at the bottom here that goes over translucency. You can give it screen space reflections, and it gets accurate reflection, it gets really cool, but it gets much heavier. And you can set the lighting mode, and there's different lighting modes in Unreal. These have an impact on performance, so you want to be aware of that. And on render quality. The first one is the cheapest one, non-directional volumetric. Per vertex, non-directional is pretty much more or less the same, but slightly differently done. But so forward shading is the heaviest, but the nicest looking one. So you really want to manage that, and just want to bring that to your attention. Good. And we're almost there, ending up with post-processing now. So the interesting thing with Unreal Engine 4, and even Unreal Engine 3 actually had this, is that by default, pretty much all of the post-processing is enabled. This is not an additional layer you got to enable, or you got to add to the, it's not a plugin, it's not, nothing like that. It's everything is there, pretty much by default, some exceptions aside. That means that as you're working with your game or your project, you're gonna turn certain features off or tweak them, but they're already enabled. And then you optimize as you go along, but you immediately get the best visual quality with everything there. And most of these are very straightforward. So I'm gonna do this fairly fast, but I wanna highlight what's maybe unique to Unreal and more specific. So here's all the things we've got. And as we go through, we got Tonemapper support. And by the way, before I even do that, just to highlight where this is coming from, all of these are in a post-process volume. Typically, they are in the post-process volume. You can put them in a camera, you can put them in a post-process component, but typically a volume is what we use most.
Or the project settings.
Or project settings, so there's other places. But there is a volume. The volume would allow you to maybe define a region where there's different post-process settings. So in this box, this region, inside the building, for example, it feels more blue. So we have tone mapping that makes it darker. Outside, it does something else. But there's also a setting. You can see this is the box, and obviously we're not in the box right now. But in this case, there is a property that says infinite extent unbound. If you enable that, this just affects the entire world regardless of size. So typically I have one of those, and then we might have some unique ones placed in specific places where we need to override it. And all of the settings are in here. You see there's a lot of stuff in here. It's all there. It's all standard enabled, more or less, or ready to go at least. And you can tweak all these things as you go along. But to go back to the overview, we got standard tone mapper. I don't have a huge amount to add there. It does a tone mapper. It does color correction, tint correction, or contrast, anything that direction. Maybe lesser well known is the fact, and it's also, I believe, not in the post-process volume interface, that there is a sharpen effect. You can do r.tonemap and sharpen, and you can sharpen view. So now it's much sharper. Well, this is a little bit extreme what I've done here. Typically, something like 0.5 adds a nice little extra layer of crispness on top, so it's always cool. But still, it's a tone mapper. Bloom, In Unreal, you got standard bloom, you got convolution. Convolution is higher quality, but it's more expensive. So typically in games, you would use it. It's going to be standard bloom. And the bloom in Unreal is multi-stage. So it's going to capture the, it's going to generate multiple blooms, so not just this bloom. It's going to do this kind of bloom, this kind of bloom, this kind of bloom. And it's going to blend all of them together, and that becomes the final image. So it's actually a layered result. And you see this reflected also in the properties. And if you control it well, it gives you more richness. You can see in the bloom setting in advanced, you say size 1, 2, 3, 4, 5, 6. It does 6 different passes. So you can have like one tiny bloom and one very wide bloom, and you get a blend between the tiny bloom and a wide bloom in one. And you can set the color and intensity for each of those. You got screen space AO. It is what it says it is. It's I don't have much to add there. So that's standard enabled. There is the SSSS, 6 times S. That's the fun one. Screen space, subsurface scattering. So that, it's always a fun one. And then you got the Burley SSSSS. Great. So again, it's a screen space effect. Typically used for skin, as the picture here implies. Maybe wax on a candle, but it's more meant for, I would say,
leaves.
Humans and yeah.
Well, leaves, vegetation.
Leaves, maybe, yeah. Leaves.
Depending on the quality. Yeah.
There's different ways of doing that, yeah. You could do just the material subsurface scattering, but yeah, possibly, yeah. So there's that. There's also screen space GI that was added fairly recently. It's not active in or seen it in our example here yet, but it will try to approximate the global illumination through screen space. So it's just essentially a Photoshop effect, if you want to call it very bluntly, and try to approximate that. It works quite well actually, but it's you could experiment with it and see if it works for you. I believe it's off by default, if I remember correctly. One of the few ones that are actually off by default. There is depth of field, speaks for itself. There's 3 different types. We've got Gaussian, bokeh, and circle or cinematic. If the bokeh one is the expensive one. It looks nice, but it's expensive, and we're going to remove it at some point because the circle or cinematic depth of field has taken over. Looks good as well, runs much better. Okay, but Gaussian is a low quality one. It's typically what you would use for games, or if performance is a concern, then Gaussian. If you really are after performance. Okay, but all of this is straightforward. Again, there is not much more to it than just going through the properties here and setting all of that up. So I think it'll speak for itself. So where I want to get to is the end here, but let's go through this first. There is exposure. It's enabled by default. So again, something to be aware of because you will hit that right away. You can see here in the settings also it says exposure is going to use the game settings and not the value I type here. And in the post-process settings, it will have somewhere in here it's going to say exposure, but I forgot exactly where. Exposure. And I basically clamped it. I put it to 0, 9, and 1.25, so it's barely moving up and down. But something you can work with. You can define a curve for it as well, and how quickly it changes. And then we get to the cool part. Okay. So blendables. A blendable is you use the material editor to modify the post-processing. It's insanely powerful and fun to work with. And we use this all the time for different things. The most common and visible and easiest to explain one would be water, for example. You can see we got a tiny pool of water, just for the sake of example. If I go into the body of water, you see, but if I don't use lighting, it looks the same. This is what it would look like if I wouldn't have post-process material. Because inside the body of water, see, this is why I typically make a shortcut to height static meshes to make this a bit easier. But in the body of water, there is actually a post-process volume, a local tiny volume, and that one has got a post-process material set, which is a material. In fact, it is that material over here. That is a normal standard material, but it's been configured to be a material domain post-process, which means it doesn't do anything but have emissive, and it allows you to take scene texture post-process input 0, which is the final rendered frame, so the frame as is, and you can modify that, do stuff with it in the material editor, and then pass it back to the screen. This is what gets rendered. So this is the render. So this is super cool to experiment with. We've done a couple of things here. This is going to distort the screen. You can kind of see the preview on the left already as well, because it shows you what's happening there. I think I added some distance fog. I made my own distance fog somewhere in here. I mean, scene depth is here. This adds a blue color on top of it. So using these blendables means that if you go in the water now, it looks distorted. In fact, if I move the box out, you see if I go in, you get that. The fact that it's clamped to a certain height is because of something I've done in the material. I just clamped it in the material to not display over a certain height. It's just a material thing. Otherwise, it would have covered the whole screen. But now I get that. It's just fake. So this is super powerful. I've used this to do my own color correction over the years. At times when I wanted to do something very specific, I've seen people do very stylized looks with it. So those are uses for it. Anything you wish. Heat effects and cold effects and anything like that.
To change the state of the player.
Change the state of the player, maybe. Yeah, maybe if he gets hit by a weapon or something, some kind of damage, flash of red or something, all of that could be a blendable. So it's very powerful. And then there's also other camera effects, and these are kind of similar. It's a camera effect. I mean, blendable is basically a camera effect, but they're built-in ones. So these are built-in effects, always part of the engine. You can enable grain, vignette, lens flares, dirt mask, and chromatic aberration. It's always a fun word. There is not that much to say about those, though. You essentially just enable them. They're not enabled by default, but they're all still in the post-process volume. And that's essentially it. You can do lens flares. You can see now we have a lens flare here. So that's it. There is not much more to it. Also, just a very important note there. You see there's a lot of checkboxes in front. Just because a checkbox is off doesn't mean it's actually off. It just means the override of the volume is off, not the feature is off. That's a very important distinction. The true features are on and off dependent on the RC vars that you can type. So if you were to look for SSR and you would say SSR quality is 0, you would actually kill SSR in its entirety. Then it's truly off. And this is also set in the project settings, I believe, and so forth. So that's where it truly comes from. The volume is just overrides, primarily. Okay. Okay. And then we have rendered the frame, but we have a... What, sorry?
Slides.
Yes, the slides. We've rendered the frame, but we'll get to final... we have to get to performance. So there's a few things here, and we've essentially they're similar to, or the same even, as the one that we've covered in the world building. So if you haven't seen these yet, make sure you take a look at what we've covered in world building, because they're the same ones, but again, it's world building, rendering, it's very closely related. So this is equal to, but what I do want to highlight here, which we didn't cover in the world building one, is this. And this is insanely powerful. This is the very heart of what we have. These are the C-vars, that's all. And the C-vars are all the things that you can type in console. So if you bring up the console, it's typically the tilt key underneath escape, but if you're on non-American keyboards, you could also do developer tools, output log. You get the output log, and the box here at the bottom is the same thing. So R dot, and you get a whole lot of commands. You get a lot of them. See, these are the C-vars. Everything to do with rendering is R dot rendering dot, and you got all of those settings, and you can tweak all of them. That gives you the scalability. That gives you complete control on the performance of your project or of your game. And on different devices, you can say on this device it should have this turned off. On this device it should have that turned off. It's down to the extreme that you can actually type help at the bottom, and if you press that, it would generate you an HTML file you can just open in your browser, and that's going to be a long display of all the rendering commands in the that are available. I believe it's 1,183 or something like that at my last count. So lots of it, including descriptions of it, and you can freely experiment with any of this. So here's a very standard one that I typically use. Is very common shadow quality. The ones that say quality, by the way, if you say quality 0, it also means turn the feature off. So shadow quality, and if you look for anything to do with shadow, just look for shadow, get a long list of things. I do quality, so r.shadow quality. If I enter it without a value, it will actually tell me at the bottom what it's currently set to. It's currently set to 5, so I know the current value. So if I know the current value, I can say, okay, well, let's try 4, or rather, let's try 0. So I do 0, enter, all the shadows are turned off. That's really cool. And you can't mess this up. If you close the editor and you restart it, whatever you've been typing, it'll just be reset. So you can't be afraid that you're going to type something weird and you're going to mess it up. Do whatever you want. Reset is restart means reset.
There's another set of console commands that are show that are also pretty useful.
Yep.
Like show post-processing, show and such.
Yeah, so indeed, any feature you got in general, you can do show or show flag, for example, and you can turn things off even while the game is running.
Yep.
So let's actually run the game here for a second and then see what happens. And that's great for checking performance and seeing how this goes, because even while the game is running, you can say, okay, well, you know what if r.shadow quality is 0? Does it run better? It probably runs a lot better, but you can then also indeed, as you mentioned, say show, I don't know, show, what do we have here? Something simple. Bloom maybe. See, I disabled the bloom now. It's with bloom, that's without, and you go through all the stages and see how it works out. Is it better? Is it worse? Or to debug it or anything.
Yep.
That's really cool. But that's still not all of it, because that brings us to the really important bottom part here, this example. And it's difficult to grasp some of this in in schematics and all that. So this is really just an example. When we get to scalability, again, we have over 1,000 settings available, and how it could look, if you try to sketch it out, is that you're working on a PC and you got the editor, right? And then it branches out. So you would be able to say, on a mobile device, on an Android device that is an Adreno 200, you would need forward shading enabled, you need mesh slots to be forced to a certain value, you need this set. So you can set 1,000 different properties for that one particular device and 1,000 different properties for the next device. And you really, split it up like that. And that is massively powerful. This is being set by the device profiles. So there's a thing here called device profiles. And this allows you to pick all those different devices, and you can say, these are the CVARs I want to set. So on an iPad 2, I would like to say, rendering, I want to say, I'm going to do plus here, I'm going to do shadow quality. I'm going to say shadow quality on an iPad 2, doesn't, devices, very old, older, I'm going to say shadow quality 0. But on an iPad 3 or whatever, it's going to be shadow quality 1. You really build it up exactly as you see fit. All of this, by the way, in turn, is actually going. It's just an interface for the config files. So you don't have to use the interface, just do it by hand, doesn't matter, it's just the right config files. So if you were to look at the project as we have it here, you can see there's a folder here called config. Actually, let me just double check I have, yeah, look good. Config, and these things over here, this is where it writes to. In particular, it would write to device profiles. And I'm not sure if I did an iPad Air 2, but I think I did that one. I've got a shadow quality 0. I'm not sure. Let's see if I have an iPad. There's an iPad 2. And it should show up somewhere in here. I think I might need to set it as default, or I'm not sure where I'm at. But you can also manually add the stuff over here as well. Same thing. And that's a very powerful feature. And it really aids scalability in what we do. And some things go very far, by the way. There are CVARs to force the mesh lots. So you can say, on this device, never show a lot higher than 1. Don't show lot 0. You can force material quality. You can say all materials should take a different path, a different branch that's built into the material graph. You can force particles to run at a lower lot, not by distance, but always fall back to the lower lot. You can set a view distance multiplier, which takes all distances and multiplies them. From foliage distance to lot distances, to any other distance that exists, everything suddenly gets multiplied by that one number. You can do foliage density multiply, so suddenly you got less grass, but only slightly. Everything is there. Material can be set to fully raw. There's a lot.
And also the engine can do for you, instead of doing device per device, you can ask the engine to calculate the power of the machine that is running on, and then set different levels of power and decide what settings should be using.
Yeah. Yeah, so even if you type grass, for example, you get a lot of stuff that controls the grass in front of us. It's all driven by text. It's all by console. So it's super cool.